What's up everybody, welcome to another video and hope you're ready to flex those brain muscles. This video is a continuation of my series on proof methods. So I made videos on direct proofs, proof by contrapositive, proof by contradiction, and now in this video I'm going to talk about the proof by induction method. So first I'm going to start with an introduction. I'm going to talk about when we use this proof method, how this proof method works, why it works, as well as introduce some important vocabulary words. Then we're going to jump into 3 different examples. We're going to prove 3 different statements using this proof by induction method. So I hope you enjoy and hope you get something out of this video. Whatever your purpose is for being here, I hope I help fulfill that purpose. So let's jump right into it. Proof by induction. So first let's answer the question of when. When do we use this proof by induction method? Well, we typically use this when we want to show that a statement is true for each n in the set of natural numbers or positive integers, same thing, whatever you want to call them. So let's consider this statement as an example. 1 plus 2 plus all the way up to n, basically the sum of the first n integers is equal to n times n plus 1 all over 2. You've probably seen this before as a formula, but we can actually prove it using the proof by induction method. And that's because we want to show that this is true for each n in the set of natural numbers. That's what makes this a great candidate to use the proof by induction method to prove, okay? So now that we've answered the question of when, let's dive into the question of how. How does this proof method work? Well, to do this, so to prove this statement, Pn, we first show P1 is true. And now let me just say something about this notation. P1, Pn, Pk. This notation is used to formalize the principle of mathematical induction as well as the proof by induction method. When we're actually out in the wild, actually proving things, we typically don't use or see this notation. So if you've never seen it before, that's okay. And if it's confusing to you, that's okay as well. It was for me when I first saw it. That's why I tried to include some details in these parentheses to hopefully clarify what exactly it is we're talking about. So what does it mean to show that P1 is true? That just means we want to show that this original statement is true when n equals 1. So we're just going to replace n with 1, or plug 1 in for n, however you want to think about it, and show that this is a true statement. And it turns out what we're going to be left with, which we'll do in a second, is 1 equals 1, which of course is a true statement, right? So this step is often called the basis step, and this process is often called establishing a basis for induction. So some important vocab words there that you may hear. So we continue from here by proving the conditional statement Pk implies Pk plus 1 is true for any k in the set of natural numbers. So this is a conditional statement, so it's of the form if, then. So hopefully you're familiar with these. If you're not, I have a video on them. I'll link right up there. But we want to prove this conditional statement is true. And what this means in words is that we want to show that if the original statement is true when n equals k, where k is just some arbitrary natural number, then it must be true when n equals k plus 1, right? And we do this actually by using the direct proof method. So we kind of have to understand a little bit about the direct proof method in order to use the proof by induction method. But essentially how that works is that we assume the premise is true and show that the conclusion is true, right? So we prove this directly by assuming the statement is true when n equals k, because that's what our premise is, right? So we assume the statement is true when n equals k, and then we show it must be true when n equals k plus 1. Hopefully y'all can see this over here. So this assumption that we make is often called our induction hypothesis, when we assume the statement is true when n equals k. And this whole process is often called the induction step, or sometimes we call it verifying the induction step, okay? So now that we've covered the how, let's talk about why. Why do these steps together prove that our original statement is true for every n in the set of natural numbers? Well, to think about this, I'd like to kind of zoom into this conditional statement here and think about what it means for this conditional statement to be true, right? If we prove this conditional statement is true, what we proved is that if our original statement here is true for some n in the set of natural numbers, then it must be true for that natural number plus 1, right? And since we've already shown that the original statement is true when n equals 1, the truth of this conditional statement implies that the original statement is true when n equals 2, right? But that means that if it's true for n equals 2, it must be true for n equals 3, based on this same conditional statement. And we can repeat this over and over. If it's true for 3, it must be true for 4. 4 implies 5, etc. And sometimes it's described as like climbing a ladder or like a domino effect. We're tipping over a bunch of dominoes. But essentially the idea is you can give me any natural number and I can repeat this process until I eventually show that the statement is true for that natural number. And because of that, we can conclude that the original statement is true for each n in the set of natural numbers. So hopefully that makes some intuitive sense. We're going to go ahead and continue to our first example of proving this is true. But in general, there are 3 main steps. Basis step, we show the statement is true when n equals 1. Then we assume the statement is true when n equals k, and then we try to show that that means it must be true for k plus 1. So 3 main steps, and we're going to do it right now with this example. So we're going to start this proof off the same way we start off any proof by induction, which is with our basis step. And remember, this just means we want to show that this statement is true when n equals 1. And this is usually very easy to do. So if it feels easy, it's good. It's supposed to be pretty easy. So when n equals 1, what do we have on the left-hand side? Well, we just have 1, right? The sum of the first 1 natural numbers, that's just 1. So what do we have on the right-hand side? Well, we have 1 times 1 plus 1 all over 2, which is equal to 2 over 2, which equals 1, right? So very easy to verify that. And what you want to do if you're writing this out formally and like turning it in or on an exam is you'd probably want some kind of concluding statement. Like, therefore, we have established a basis for induction, or therefore the statement is true when n equals 1, something like that. But I need all the board space I can get, so I'm just going to go to induction step. This is our next step, and I'll leave you to write that out. So our induction step, we sort of broke it up into 2 parts. We start with our induction hypothesis, right? We assume that this statement is true when n equals k, where k is just some arbitrary natural number. Then from there, we want to show that that implies that the statement is true for k plus 1. So let's start with our assumption. And I like to use the word suppose. Makes you sound fancy. So suppose the statement is true when n equals k. So I'm just going to replace n with k. And suppose this is true. K times k plus 1 over 2. And if you really wanted to be precise out here, you would write for some k in the set of natural numbers. But usually when you write this out, people know what you mean. They know you're talking about just some arbitrary k. Okay? So let's see, where do we want to go from this? Remember, we're taking this assumption and we're trying to use it to show that the statement is true for k plus 1, right? When n equals k plus 1. So what I like to do is at the bottom here, or off to the side, or at the top, really whatever, wherever, but I'm going to write it at the bottom, is use this notation want to show, right? So we want to show that the statement is true for k plus 1. So let's write out what exactly that looks like, because often when we write out what we want to show, it often helps us see how we're going to get there. And I'll show you what I mean right now. So we're going to write out what we want to show. So this is replacing n with k plus 1. We have the sum all the way up to k plus 1. And on the right-hand side here, we have k plus 1 times k plus 1 plus 1. That's k plus 2, right? K plus 2 all over 2, okay? So this is what we want to show, and this is where people often make a pretty big mistake. What you often see people do is they'll make their assumption, they'll write out what they want to show right under their assumption, and then they'll start manipulating what they want to show until they get to a true statement. And this is not how we should be working out induction proofs, or really any proofs for that matter. We should never start with what we're trying to show and work with that. We should always start with our givens and our assumptions and finish with what we want to show. So if you want more details on why this is incorrect, I had a full discussion about it in another video. I'll link it right up here. But we're going to do it the proper way, the formal way, right? We're going to be precise and start with our assumption and work toward what we want to show, okay? So how can we get there? Well, we can notice that the only difference, at least on the left-hand side of these equations, is that here we have a k plus 1 added, and here we don't. So since we're assuming this is true, that means I'm assuming that this equals this. That means I can add k plus 1 to both sides, and they're still equal, right? I'm adding the same natural number to both sides. So I'm going to go ahead and do that. So I write a forward arrow here. So this implies that 1 plus 2 plus k plus 1. I'm just adding this k plus 1 to both sides. This implies that this equals, well, what do we have here? K times k plus 1 over 2 plus k plus 1. And now I have the left-hand side of the equation exactly like the left-hand side of what I want to show. So all I have to do is take this right-hand side and show that this equals this right-hand side. If I can do that, then I'm done. Then I've shown exactly what I want to show. So let's take this and manipulate it. What I'm going to do is find a common denominator. So this equals k times k plus 1 over 2 plus 2 times k plus 1 over 2. And now let's see what happens when I combine these. So I'm going to combine these two terms now that I have a common denominator. I have k times k plus 1 plus 2 times k plus 1. And maybe you already noticed the common factor in both terms. Because what I can do is I can take this factor of k plus 1 and bring it out in front, right? I factor out the k plus 1, and what I have left is k plus 2. So what I have left is, I bring the k plus 1 out in front, factor it out in front. I'm left with k plus 2, and this is still all over 2. And you'll notice that's exactly what I wanted to show, that this was equal to, right? So since I have these string of equalities, right, this expression equals this, equals, that means that these two things are equal, which is exactly what we wanted to show, right? So we started with our assumption, we manipulated our assumption, not what we want to show. We stuck with manipulating our assumption until we resulted in what we want to show. And therefore, we can say that the statement holds for k plus 1, and then our concluding line would be something like, by the principle of mathematical induction, the statement is true for all n in the set of natural numbers. So hopefully that makes sense. Let's go ahead and jump into an example. This one's a little bit more difficult. So this proof is similar to the last one in the sense that we have another sum, but it is a little bit more involved. But what I encourage you to do, if the last example made sense, pause the video and try this on your own. If you get stuck or if you want to compare your work with my work, then you can press play. Challenge yourself a little bit. So we're going to start out the same way we always do, basis step. Let's let n equal 1 and see what we have. Well, on the left-hand side here, we have 4 times 1 minus 3. 4 times 1 minus 3, that's just equal to 1, right? On the right-hand side here, we have 2 times 1 squared, that's just 2, minus 1, which equals 1. So these two things are indeed equal, and we have verified or established a basis for induction, right? So write some kind of concluding statement there, therefore the statement is true when n equals 1. And now let's get to the real exciting part of the proof, the induction step. We're going to do the same thing we've been doing. We're going to assume. I'm going to use the word suppose. Suppose that the statement is true when n equals k. So suppose 1 plus 5 plus 9 plus all the way up to 4k minus 3 is equal to 2k squared minus k. And now let's write out what we want to show. Because remember, we want to take this assumption and we want to use it to show the statement is true for k plus 1. So want to show, let's see, what do we want to show? 1 plus 5. I'm going to have to skip the 9 because I feel like I might run out of room. But the 9 is somewhere in that ... okay? 4k minus 3 plus... Okay, let's see, what do we have here when we plug in k plus 1 in for n? Let's do that off to the side here. There's absolutely no shame in doing this, by the way. This is what we get when we plug k plus 1 in, right? So we can simplify this to 4k plus 4 minus 3, which is 4k plus 1, okay? I would rather double check than write something down that's wrong and spend 30 minutes trying to prove something that I can't prove because I copied it down wrong, right? So no shame in double checking. Just do some scratch work off to the side, then erase it and no one will know it ever happened. So we want to show that this equals what? Well, what do we get when we plug k plus 1 into here? 2 times k plus 1 squared minus k plus 1. Okay, so this is what we want to show. So we can again notice that what's the difference between our assumption and what we want to show? Well, on the left-hand side, the only difference is this 4k plus 1 being added, right? So similarly to the last example, we can take this equation, since we know that these two things are indeed equal. That means if we add 4k plus 1 to both sides, it's still true. They're still equal. So I'm going to go ahead and do that and see what we get and see if we can go from there. So I'm going to draw this little arrow here. 1 plus 5 plus, I am going to delete the 9 again just because we don't really need it. It's in those dot, dot, dots somewhere. This pattern continues up to 4k minus 3. And then we're going to add 4k plus 1. And we got to do that to both sides. So 2k squared minus k plus 4k plus 1. So now we can get rid of the parentheses, we can start combining, we can start doing all that. But what I really like to do before I start messing with this, because it's not obvious to me how we're going to make this right-hand side look like this. Because we already have the left-hand side exactly how I want it. All I really need to do is take this right-hand side and show that it's equal to this. But that's not obvious how to get there. So this is when it really benefits us to write out what we want to show. Because what we can do is we can work backwards a little bit, but only if it's with the intention of figuring out how we're going to get from here to what we want to show. Hopefully that makes sense, right? So we're going to treat it as scratch work. We're going to undo this a little bit, see if we can make the connection between how to get from here to here, then erase it and complete it from forward to the end. Hopefully that makes sense. You'll see exactly what I mean. I can multiply out this k plus 1 squared, and what I get is k squared plus 2k plus 1. And this is minus, and I'll just get rid of these parentheses, so I got to distribute that negative. Minus k minus 1, right? So now let's distribute this 2 in here. 2k squared plus 4k plus 2 minus k minus 1. So this is for sure equal to this, because I just undid it a little bit, right? Now let's compare this with what we have here. We have a 2k squared, we have a minus k, we have a plus 4k, but here we have a plus 1. Here we have a plus 2 and minus 1. But wait a minute, that's the same thing as plus 1, right? 2 minus 1 is equal to 1. So if we can take this, rearrange it a little bit, and rewrite it in this way, then we can continue forward, eventually showing that this is equal to exactly what we want to show. I know it feels like cheating a little bit. I guess it kind of is, but this is how I like to do it. Undo it a little bit until you recognize how you're going to get forward, then erase and continue forward, and everyone will think, whoa, how did you get from there to there? You're a genius. It's a great thing. So, equals 2k squared plus 4k. I'm just going to rewrite it in this exact way because we know that these two things are equal. Plus 2 minus k minus 1. Okay? So this is for sure equal to that. My next step is going to be to factor. And really, I'm just going to factor twice, I guess. This is equal to, I'm going to factor out the 2 out in front. And I guess you could maybe do this all in one step. And then brought the negative out in front. And now my last step is just factor this. And now what do we do with this scratch work? Erase it. It's like it never happened. So now we look like a complete genius, because how did we know to rearrange this in this way? Well, we're just really damn smart, but that's not really it. We did some scratch work, we worked backwards, and then we were able to get from our assumption to what we want to show. And I think this is why so many people start with what they want to show and undo it, because it is easier. But just because something's easier doesn't mean we should do it versus something that's correct and more precise, right? So I've kind of found this middle ground where we can work backwards a little bit as long as we make sure that our final product, our final proof, is working with our givens and our assumptions toward what we want to show, right? So what we've shown is that when we assume that this statement is true for some arbitrary k in the set of natural numbers, then that implies that it is true for k plus 1, right? And therefore, by the principle of mathematical induction, the original statement is true for every n in the set of natural numbers. Let's do one more example. All right, so here's the last example for this video. We're going to prove that 7 to the n minus 4 to the n is a multiple of 3 for each n in the set of natural numbers. So I think this is a fun one to finish off with. And let's go ahead and start with our basis step. We want to show that this statement is true when n equals 1. So when n equals 1, what do we have? 7 to the first power minus 4 to the first power, which is equal to 3. So is 3 a multiple of 3? Yes, of course. 3 times 1 equals 3. So therefore, we have established a basis for induction, and we can move on to the fun part, which is the induction step. Okay, so in the induction step, we're going to assume that this statement is true when n equals k, where k is just some arbitrary natural number. So I'll write, suppose that 7 to the k minus 4 to the k. And how do I express this as a multiple of 3 mathematically? Hopefully you remember this. Well, that means it's equal to 3 times some integer. So I'm going to use the letter m, where m is just some integer. That's what it means to be a multiple of 3, is that you can be expressed by 3 times some integer. So we're assuming this, and we want to show that 7 to the k plus 1 minus 4 to the k plus 1 is a multiple of 3. So let's write it out down here. And you don't have to write what you want to show at the bottom. I'm just doing that to be consistent. So we want to show that 7 to the k plus 1 minus 4 to the k plus 1 is equal to, what do you think, 3m? No, right? Because that's what this is equal to. We just want to show that it's equal to 3 times some integer. So we definitely want to use a different letter there. I'll use L, where L is just some integer, right? Okay, so this is what we want to show. And now how I'm going to start this proof is in a way that may seem like it's contradicting some of the things I mentioned in this video, but I'm going to explain why it doesn't. So we're going to say then, and I'm going to write out what we want to show. 7 to the k plus 1 minus 4 to the k plus 1, so plus 1, equals, and I'm just going to take this expression and I'm going to manipulate it, change it around a little bit, and eventually show that it's equal to 3 times some integer. So why is this different? Why is this not assuming something that I shouldn't be assuming? Well, in the last 2 examples, what I wanted to show was an equation. And what I would have done if I would have written out that equation is I would have assumed that that equation is true and manipulated both sides and worked with it, which I can't do because that's what I'm trying to show. Whereas in this example, we can just simply take this expression and start dealing with this expression and showing that it's equal to a bunch of different things and eventually get to 3 times some integer. So that's kind of the difference. Equations, you never want to start with. Expressions, you can just say, sure, let's consider this expression and manipulate it a little bit. This is how we prove trigonometric identities in pre-calculus. That's why they tell you don't work with both sides of the identity to prove it, because in doing that, you're assuming the identity is true already, right? You pick one side and you say, well, let's take this expression and you show it's equal to the other side. That's similar to this idea. Hopefully that makes sense. I don't want to confuse anybody, but we're going to take this and first we're going to use our exponent rules. We can rewrite this as 7 times 7 to the k minus 4 times 4 to the k. And now it may not be clear as to how we're going to show this is equal to 3 times some integer. So if you want to pause the video and take some time, that's fine. But what we're going to always want to do in these divisibility proofs is use our assumption. And really in all these proofs, we want to use our assumption. So eventually we need to get to a point where we can somehow factor out a 7 to the k minus 4 to the k and rewrite that as 3m. So I'm going to work toward doing that. Let's see if I can separate this and maybe write 7 times 7 to the k as 3 times 7 to the k plus 4 times 7 to the k. Because what that's going to do is it's going to make these coefficients the same so I can factor out a 4. Because now what this is going to be equal to is 3 times 7 to the k plus 4 times 7 to the k minus 4 to the k. Let me make sure that that's right. 3 times 7 to the k plus 4 times 7 to the k minus 4 times 7 to the k. Factor the 4 out in front. Yep, we're good to go. And this is equal to 3m. That's our assumption, right? That this is equal to 3m. So this definitely equals 3 times 7 to the k plus 4 times 3m. And remember, what we're trying to do is show that this is equal to 3 times some integer. So what I can do to work toward that is maybe think about how can I factor 3 out in front and have an integer left inside of parentheses. And I see what I can do here is just swap this 3 and the 4, right? 3 times 4 times m is the same as 4 times 3 times m. We could swap it back and forth. So we have 3 times 7 to the k. And I'm just going to make that little adjustment there and rewrite it as 3 times 4m, because what that allows me to do is factor the 3 out in front of this expression. Now what I can do is write this equals 3 times 7 to the k plus, let's see, 7 to the k plus 4m. Sorry, I got lost on where I was. Plus 4m. So now all we need to show is that 7 to the k plus 4m is an integer. If we can show that, we're done, okay? Well, k is a natural number, so 7 raised to some natural number power, that's definitely an integer, plus 4 times m is an integer, so that's an integer. The sum of two integers is an integer, so we're good to go, okay? And again, we haven't assumed anything that we shouldn't be assuming. We just considered this expression, manipulated it until we eventually got that it was equal to 3 times some integer. The only assumption we used was the original one that we made. So we've showed that this statement being true for n equals k, where k is some natural number, implies that it's true for k plus 1, and therefore we've completed the induction proof. This one's a little trickier. If you don't fully understand it, that's okay. Pause the video, rewind it, try some more examples on your own. This stuff is not obvious at first. It does take some time, but it just takes practice doing it over and over again. Hopefully this video helped, whether you're in an intro to proofs class or you just want to get better at proofs. Hopefully you enjoyed it. Like and subscribe if you did. Most importantly, keep flexing those brain muscles, and I'll see y'all later.